All right, let's get started, everyone. We are going to continue our description, our introduction to linear regression, or I should say linear methods in regression. So let me review what we had already introduced in our last lecture. We have introduced our classical linear model. Now, this model, hopefully by now, is as boring as hell, right? Hopefully. So we had y is equal to W0 plus x1 W2 plus, W1 plus x2 W2 all the way to xp WP. So I have x is, say, in the real domain of p dimensions, right? And y is my output variable that, as we will see, can be of, say, q dimensions, right? Whatever dimensionality that corresponds. So y is a function of x and my vector w, right? And my vector w is nothing else than all these parameters that I have of my function, okay? That defines my function. So w is w0 all the way to wp, okay? So generally, we don't write it this way. We write y of xw is equal to w0 plus the sum over j, let's say, of wj phi j, or actually, let me just write xi here, or xj, excuse me, xj, right? And now a couple of substitutions that we have introduced. One is we can extend this linear model, making it still linear, right? But we can introduce a functional mapping. So now introduce a functional mapping on x, right? Such like, for example, phi, right? That maps from Rp to some other space. Let's call it, it could be of the same dimensionality, it could be of different dimensionalities. We'll say K for now, so that we can now extend this model to y of the sum of wj phi xj, okay? And here I have made an additional application, right, or an additional simplification, excuse me, right, that I have eliminated this w0 as I did last time, right, and that I can do by simply imposing that my my phi j of x0, right? So it'd be rather, so that phi of x0, let's eliminate that. Yeah. Phi of x0 is equal to 1, right? And if we do that, it allows me to do the simplification. So that's the equation that we had derived last time. Okay, so far so good? Everyone? Yeah? The back? Yeah? All right, great. So we discussed several functions. These are called the basis functions. Anyone can tell me why they're called the basis functions?
Does that define space, the functional space?
That is what defines the space, right? The basis functions, in the same way that the basis vectors define my underlying feature space. This defines the underlying functional space, right? And these are my basis functions that I use to do so. And that's what allows me to use this linear model by using basis functions that may be linear or nonlinear, right? So the classical linear function, or classical linear functions could be phi of x. Obviously, you could see phi of x equals to x, but most typically you will see x transpose x, right? The inner product being called just a linear mapping, right? Linear basis function. We've discussed other functions. Phi of x equals, say, phi j of x equals the exponential function, right? An exponential e to the power of negative x. Whoops, my bad. Negative, let's see, x minus mu j square over 2 times the variance. Okay? Anyone remembers what this is called? This basis function? The Gaussian? Very good. This is the Gaussian basis function. Okay. And obviously mu, remember the mean, sigma the variance, right? Hopefully by now we don't need to keep repeating these terms. Other ones that are very popular are, for example, this one, phi of j of x, it's equal to a function f of x minus mu j over sigma, where f of a, it's equal to 1 over 1 plus the exponential of negative a. And this is called, anyone remembers? What's that? Yeah, the sigmoidal is fine, but what was that? The logistic sigmoidal, okay. Okay. Good. So that's what we have. And now our goal is to find, as always, to find the value of the parameters of this model, right? So I have this model right here. Well, actually not this one, excuse me. This one right here, right? And I want to find the parameters of this. How do I usually do this? Do estimation. What do we do? Compute the what? Maximum likelihood estimator, right? Very good. So maximum estimation. Let's see how this would work. So let's see. Let's define our target function. Our target function, I'm going to define it as, let's say, t for target. It's equal to y of xw that I have there plus some error, okay? Some epsilon. That defines my error. And to simplify things, I'm going to assume that my error is normally distributed, right? Distributed according to a normal distribution, as we usually assume, with zero mean. So it's a zero mean error. And maybe we'll do beta inverse as my variance, okay? Okay, so zero mean Gaussian noise with beta inverse as my variance. Okay?
It's scalar,
Yeah, just a variance, 1 over beta, right?
but the whole vector, the epsilon, is it
Oh, if it's one-dimensional, it's just one value, right? But if it were to be multiple dimensions, we'll get there, then it's going to be more than one. Then it's going to be a covariance matrix, not a variance. Very good question. Okay, so we need to provide a model for f, right? I'm sorry, for t, not for f. For t, right? That's what we always do. So let's see how we can model this. We're not going to do anything new. We're going to do what we always do, right? So we're going to define a probabilistic model. So the probability of t, right? My variable that I need to estimate, given x, obviously, which is my observation, right? W, which are my parameters, and the noise, beta, okay? Beta defines the noise, right? The normal distribution of the noise. It's the only parameter. Okay. And that we're going to model using a normal distribution. So this is going to be a normal distribution with, say, t, y of x, w, and beta inverse, okay? Right? Okay, excellent. So now, what do we want to do? Well, we need to use a specific loss function to compute this, right? And to compute the expectation, usually we have used before which loss function? Anyone? What's that? The 2 norm, which is called the square loss, right? So the square loss. So then if I use a square loss, my expected value of t given x is given by, I integrate over the whole space of t, probability of t given x dt, right? And what is this equal to? Well, that has to be equal to my observation, my result, yxw. Okay. So this is, of course, the unimodal estimate. Unimodal by meaning that they only use one mode of a normal distribution, right? I'm not going to do this here today, but obviously you have it in the notes that I posted in Canvas. You could model this with a Gaussian distribution, right? A mixture of Gaussians, excuse me. So then it would be, let's see, the probability of t given the parameters of the mixture, and it would be, say, k from 1 to g, the number of modes that you add, the number of Gaussians, the prior probability of each of the Gaussians, then the normal distribution of t given y, x, w, and the parameters, right? Well, don't need an inverse here. It's a little odd. So this is just a side note to say you could model it with a mixture of normal distributions or with any other parametric method that we have used to define our densities, right? I'm going to stick with the simplest one, which is this one here, with just one normal distribution. All right. So now what do we have? Now we are given our training set, right? So we're given our training set, and let's call the training set, let's see, xi, right? And this would be All right, that's a little confusing. That's a confusing notation. This would be xi vector, this one, right? So that would be the same as saying xi in RP, and then you'd have i's here as well, right? Right? Makes sense? Okay. Because we're going to have multiple simple vectors, right, in our training. And for each of the xi's in my training set, I also need to get what? Come on. The output, which is t in our case, right? So ti. And let's say, as always, that I have n of them, so from 1 to n. OK. So given that training set, now I can compute the probability of t given, let's call this, I don't know, capital X maybe. Capital X, W, and beta, which is our variance for the noise. This is equal to the product, correct, of 1 through n for each of the samples, right, of the normal model that I have derived here of Ti given W transpose phi xi beta inverse, right? Am I right thus far? So far, so good? Yeah. And now here, of course, where t is equal to t1 through tn, right? This is the vector of our observations, and capital X, we've defined it here. Well, actually, capital X, probably that's a little misleading. Capital X, it's only x1 through xn, right? Does not include the t's, so it makes no sense. Yep. Because the t's are here, right? And the x is here, obviously. T's is what we want. The x's is what allows us to estimate t. So now let's take the log of the likelihood, right? As we always do. So this product becomes a summing term. So if I take the log of the probability of t given w and beta, then I have the sum from 1 through n of the log of my normal distribution ti given w transpose phi xi and beta inverse. Right? Only took the log of our likelihood ratio, right? I'm sorry, of our likelihood function. All right, yes, question?
Shouldn't it be like given x as well, probability of t given?
Oh, if you want, yeah, sure. Here, right? Yeah. You're right. Yep. And now we have our log likelihood function, and we want to find the estimator. So what do we do when we want to maximize, right? We want to maximize this likelihood. What do we do to maximize this likelihood? What's that? A little louder so we can hear you. Come on, what do we do to maximize the likelihood function? I can hear you. Okay, take the derivatives, the partial derivatives, or the gradient in that case, and equal it to 0, right? Okay. So now we're going to take we're going to compute the gradient of the log likelihood and equal this to 0. And what do we get? If I take if I compute the gradient, I get Ti phi transpose xi minus w transpose times the sum from 1 through n of phi xi transpose, and that equals 0. I put the transpose there. Some people put the transpose here for the function. Some people, like myself, sometimes put it here. It's up to you. No difference, just notation. So now if you rearrange the terms, we agree to that, right? That just comes from this function. Where do we have? From this one right here, right? Where the normal model was defined here, right? And now if you arrange these terms, you get the maximum likelihood estimator of W, right? You can write WMLE. You can also write it as star, as the maximal solution according to this criterion. Then this is going to be equal to, let's see, W. So I need to move this to the other side, right? To this side to make it positive, right? Or I move this to the other side. And then this divides here, right? So I'm going to get, let's see, this is, let's do this first. This is phi t, where t we have already defined somewhere here, right? T we have already defined. And now capital phi, where capital phi is equal to phi 0 x1, phi p x1, and all the way to phi 0 xn, phi p xn. Okay? So this, it's the same as this term, right? You see this? Right? If I multiply this vector by this matrix, I get this, right? You agree? And now this term has to go to the other side. Let's see. This term, I can write it as phi transpose gives me phi, and I need to inverse it, right? To move it to the other side. All right, I'm done. Fantastic. Now, does this look familiar to you, this result that we just derived right here? This result? Is this familiar to you? What? That's a pseudo-inverse, which is the same result as what? Least squares, right? This is the same as the least square solution. It's amazing. So this is a pseudo-inverse. And this, therefore, is the least square solution. Okay. So you see that doesn't matter how we do things, we always keep coming back to the same solutions over and over and over again when we use these same techniques of obviously using the okay, before I give probably the answer, I should ask, what do you think we got the least square solution? What's that? Speak up. I can't hear you. You're too far back. Speak up. Right, but my question is, why do we get the least square solution? Yeah. That's very good. That's part of the reason. You're right, but there is a more fundamental reason.
Distance in the Euclidean space, the distance.
Very good. So what did we use here? Let's put it in terminology that we can understand. What you said is correct, but let's just put it in the right terminology.
To minimize the distance between.
Right. So we use a specific what? What function? The loss function that we use was which one? The square loss. And we got the least square solution when we derived n equal to 0. Duh, right? I mean, not surprising, right? And when we use correct again, when we use the normal model, that's the same thing again, right? We're actually optimizing for the least square solution there too. Very good. So that's why. Yeah, question?
Yes, so what happens if the matrix is not invertible?
This is a pseudo-inverse, right? So the pseudo-inverse is always going to be computable.
But the B transpose B.
Right, that's always going to be positive definite, right? Or positive semi-definite, right? Obviously, by definition.
Yeah, but it can have 0 eigenvalue.
Well, if it does, you can eliminate those dimensions. They're irrelevant, right? I mean, that's a PCA solution, correct? The least square solution. If you have 0 eigenvalues, yeah, then they don't mean anything. These dimensions, it's like having this space, two-dimensional space like this, right? And all my data points are here. And I have a null space, right, of my data that doesn't represent anything. Yeah, that's like not having that dimension. That can be just simply eliminated. All right, any other questions? Wonderful. So now let's derive something extremely important for not only regression. Obviously, it's very important for regression, but not only for regression, but for many things that we will do in the rest of the course. And it's extremely important in pretty much anything that you're going to do in machine learning. We're going to extend this model that we have derived here by adding what's called a regularizer term. So regularized, we're going to call this a regularized least squares solution. Okay. That, going back to that question, it's also going to allow us to compute solutions even when there is no solution in that case that you were just mentioning. Okay. Not the sole purpose, but it will allow you to do that. Okay. So let's see how. So let's define EDW as our first error function, and I'm going to call this the data error function, therefore the D. And remember, we've defined this ED, then it's equal to 1/2 the sum of Ti minus W transpose phi xi square, right? Because we're using the square laws over every I. And this 1/2 is just a normalizing term, so that when we take the derivative, the two cancel out, and just mathematical convenience, right? So now this is obviously the least square solution, right? Because we're using the square laws here. And all this means is that we want the output of our function, right? The regressor function to be equal to the value that it should have, right? So that's the one that we have derived already. Now I'm going to add here another term. Let's call it EW of W. And this, I'm going to call it the regularizer. Or you could say the regularization term. Okay. Now, it's weird to just have these two functions added with one another, because obviously what, as you will see in a second, what you really want is to find a solution for this, right? And you're just going to regularize with this function. So we're going to add a constant here, lambda, right? Where lambda, we're just going to say it's some constant, positive constant larger than 0, okay? Now, going back to this, as you will see, this is not the only reason, right? But going back to this, there was the question earlier, what happens when this is singular, right? And it cannot compute this inverse. Then obviously, if you don't want to regularize, this is easy. You eliminate the null space, right? You compute PCA if you want, doesn't matter, right? This is easy to solve. But if we add now a regularizer like this, right? We add another term that is full rank. It has to be full rank, right? Then you don't need to eliminate any dimensions anymore, right? And sometimes that may be appropriate, okay? And sometimes it may not, right? Sometimes when you have dimensions on your feature space, they're not representative of anything. It's just better to eliminate them. Why do you want to keep them? Makes no sense sometimes, okay? All right. So what are we going to use for the EW, for the regularizer, for the regularization term? What are we going to use? Well, we can use any loss function that we want to, right? And here we go again. So for example, I could use the 2 norm, right? The square loss. So I could say that this is equal to 1/2. Again, this 1/2, you keep seeing me, or you will keep seeing me using it all the time. This is just for mathematical convenience, right? Because when I take the derivative, then the 2's cancel out and everything looks much nicer. Doesn't mean anything else than this. So let's say the 2 norm, right? I could compute the 2 norm of my vector, of my vector of parameters. I could compute instead the 1 norm, right? Oops, that's funny. The 1 norm of W, right? And so on. Any of the loss functions that we have derived, or that we have introduced rather, before, right? I could use them here. Now, this is the real reason, what we're going to discuss next is the real reason why I want to add the regularizer, right? Obviously, yes, it solves the problem of singular matrices there. But why do I want to add this regularizer? Because when I add this regularizer, I change the way I find the solution for this equation, right? Or for this part of the equation. Let's see why. Let's go back, as always, as I always like to do, to my space, okay? This is my vector space that we always work with. And now let's say that EDW, right, where we are using, remember, the square loss, right, is going to give me a set of possible values for that square loss, right? So let me write these square values like this. Remember, this is what we did when we were doing, for example, ICA, right? That we draw the norm, right, about the point where I'm at, right? And good. And now I want to find a solution that is common also with my regularizer here, right? Now the regularizer is going to be defined by, say that I use a 2 norm. It's going to be defined again by circles, by S1 here, right? Until they both converge right here into a solution, and this one right here, right, that's my solution. Right? That's a solution. Okay. But what would happen if I use instead the one norm here? Let's see. So now I would have this one as before, okay? And what does the one norm look like? It doesn't look like this, does it? It looks like that, right? Well, you know. All right, not perfect, but a little better, right? It looks something like this, correct? And if I keep growing this, right, I'm going to go to this, and eventually to this, right? And I'm going to find a solution. Actually, this is poorly drawn. Yeah, let me do this. Let me draw this better. Because if I don't draw the right thing, I'm not getting the right result. And then that makes no sense. Okay, that's a little better. And now what do I have? I have this point here, and I just start drawing circles like this, and I get my solution about here, okay? All right, so I get this solution. This now it's my solution. Okay? So what happened? When I used the 2 norm, right, as regularizer, I get one solution. Nothing wrong with that. That is a solution given by this loss function. When I use the 1 norm, I get this other solution. Again, nothing wrong with that. That's just a solution according to that new criterion that I have defined, right? This first one is the one that we are accustomed to, right? This is the one that we have defined to date, or we've worked with to date. But how about the other one? The other one, it's usually called it's a solution that leads to what's called sparse solutions. And by a sparse, it means that in many instances, you're going to get the result that I draw here, where the solution is only in one or a subset of the dimensions, but it's 0 on the other dimensions. In most of the dimensions, it's going to be 0. Let's think about why this may be. In the 2 norm, the distance of all these points on the surface of S1, right, or that define S1, are the same distance from the origin, right? That's what the 2 norm means. Here, these points are at the same distance from the origin as well, according to the 1 norm, right? But is it most likely that the point like this is going to reach that other function, or that a point here is going to reach that function? Or if the function, this other function were here, right, that this point or that point are going to reach it? Obviously that point, right? This point is getting closer and closer to anything that you can find on any of the quadrants or orthants in more dimensions, right, of your space. So not always, but typically, you're going to get solutions like this. And that's going to yield sparse solutions. Oops. Now, in particular, when we use this one norm here in regression. This is called the Lasso. Okay. So let's start with the 2 norm first. So if I use the 2 norm, then the least square solution is going to be equal to my W, let's call it the star again. It's going to be equal, well, this first term is obviously not going to change, right? It's the same solution as before. So I'm going to have phi transpose phi inverse phi transpose t, but because I have added, where is it? Right here, this regressor, I'm going to get plus the identity matrix, okay, which defines the 2 norm, right? The identity matrix, times something else. Anyone can tell me what else? The identity matrix is going to be multiplied by something. Lambda, right? Obviously. Very good. Which is a scalar that defines the size of that 2 norm, right? And now note why all of a sudden, if that matrix were to be singular here, it's no longer singular there, right? Because it's full rank. Because the identity matrix is always full rank. Right? All right. This solution, this least square solution for regular, or this regularized least square solution for regression, linear regression, is called, very famous, it's called Rich regression. Very famous solution. You'll see it used all the time. Okay. More generally, if we extend it to other norms, I'm going to have the following: 1/2 the sum over all I of Ti minus W transpose phi xi squared plus lambda over 2 the sum over all j of Wj, let's say to the power of q, okay? To the power of q, where q is larger than 0, okay? Now, if q is equal to 1, then I have the 1 norm. If it's 2, I have the 2 norm, and so on. Now, remember that between 0 and 1, I could have a quasi-norm, right? If q is between 0 and 1, here, if q is between 0 and 1, but not 0 or 1, then it defines a quasi-norm. Anyone remembers what a quasi-norm is? No? It's a function that satisfies all the properties of a norm except one. Which one? Huh? The triangle inequality, very good, which it does satisfy, but only up to scale. Okay? You need to add the scalar, right? Remember, it's smaller or equal, right? f from A to C is smaller or equal than f from A to B plus B to C, if you multiply that right-hand side by a scalar, k, right, then a quasi-norm does satisfy that. Okay. All right, and again, if I use q equal to 1, then we talk about the Lasso. All right. Now, there was another question earlier, I think here. What happens if t is just not one-dimensional, right? So I have actually, let's call it a vector capital T, let's say, of t1 through tn, right? Then, or tm, this is m. Then the maximum likelihood estimator, W star, is going to be equal to the same thing that I had here, or the same thing here if you want to add the lambda I inverse transpose times t. Okay, that's it. Same solution. There's no change, right? Any questions? Should we move on? Okay. All right, so this is rich regression. Now let's define another very famous method for regression, which is called logistic regression. Okay. It's funny because logistic regression really is not a regressor. It's a classifier. So it's called regressor. That's sort of funny. But you'll see why in a second, right? I mean, the equations are very similar. So because the equations come from a mixing of what we have seen here today in the generative approach in the last several lectures, then this is called regression. Okay, so what did we derive in the probabilistic approach? We said that if I want to compute the probability of x belonging to a class I, so pi of x, right? That's my posterior probability for class I. That using which theorem? I keep forgetting the name of that theorem. What's the theorem that we use? No one? No takers? Bayes theorem. Thank you. All right. So if I use Bayes, that would be equal to let's see, it would be equal to the prior probability, right? And the prior probability here, summing, oops, maybe that should be J. J, and now I'm going to do the probability of x, right? And for the two-class problem, I had the probability of 1 is equal to, let's see, the probability of 1 is P1 of x, P1 over P1 of x plus, whoops, P1 plus P2 of x plus P2, which is the same as saying that P1 of x is equal to 1 minus P2 of x, right? Right? For the two-class. This is for the two-class case. Right? So what we're going to do is we're going to rewrite this as a function of a variable a, which is the logistic regression function, basis function that we introduced before, which was 1 plus, anyone remembers? The exponential function negative a, right? Okay. And note that if I use now a equals to the log of P1x capital P1 and P2, right? Am I right? X capital P2, right? That's the log likelihood. Then I substitute this here and I have the exact same equation. So what I'm going to do, I'm going to write that my P1 of x is equal to my regressor that I want to compute, right? The y of x, right? My linear model that I have defined, which is nothing else than sigma of a. What's my a in my case here? For the regressor, the linear model that I have defined is my W transpose X. Yes? Right? So this here is the logistic regressor or let me call it this, regression classifier, because this is really a classifier. So, what's the likelihood function? The likelihood function, as we have done before, with ridge regression, no change, is going to be the probability of t given my weights w. It's equal to the product of all the yi, 1 minus yi, and I'm going to now, so I'm in the 2-class case, remember, I'm going to consider this a binomial function, right? This is the output of the first class, right? Which I'm going to have, say, t times, or maybe we could even say ti times, and here it's going to be 1 minus ti, and I have, or I had, as I defined before, n samples. So remember, we've defined this before, t is equal to t1 through tn, and in this case here, each ti, we're going to assume, because we're going to make this binomial, right? We're going to assume that it can only take 2 values, right? 0 or 1, okay? So that either this is true or this is true, right? Binomial. Yes. And now we have yi is going to be equal to the probability, say, of 1 xi, okay? So our regressor now is going to estimate the density or the probability of my observation. Make sense? Now, obviously, as we have done before, we can extend this with our mapping functions, our basis functions. So I can also write that, let's see, I could write I could use, why don't I change this here, right, to sigma W transpose phi, okay? Where phi is my basis functional mapping that I want to use. And in that case, here I'm going to have y of I, it's equal P1 of phi I, right, of each of the elements. Where again, as in here, phi, it's equal to phi 1 through phi n. Right? And because this is a classifier, remember, with classifiers, we like to use not the likelihood, not the log likelihood, but the negative of the log likelihood. So let me compute the negative of the log likelihood of that. So the negative of the log likelihood is going to be negative of the log of P of t given my weights W, which is equal to, let's see, negative, obviously. I'm going to sum over I 1 through n, as always. And now I'm just going to take of the likelihood function that I have on the other side of the whiteboard, right? And take the log. So it's the product becomes a sum, and I have ti, the log of yi plus 1 minus ti, the log of what is it? I think I have 1 minus yi, right? Thank you. Right? So far so good. And now remember that here where yi, we have said that it's equal to sigma ai, right? And ai is anyone? You have it written there? Anyone? W transpose x. I'm sorry, W transpose phi I. My bad. Okay, so now we can optimize the function as above by computing the maximum likelihood estimator, right? So we can compute the the gradient of the error. And our error function, as always, is we want yi to be as equal to ti as possible times phi I. Now, this unfortunately does not have a closed form solution. Because it's nonlinear, so we can use nonlinear least squares instead, right? So we need, as before, an initial estimate. And so let's call it W0, for example. And then we iterate, right, as we have done before. Many times by now, we say W at time k plus 1, it's equal to W at time k minus the Hessian inverse times the gradient of the error function of the parameters that we're trying to estimate. Now here, remember, the gradient of my function is nothing else than if I take the partial derivative of my function here, right? This is going to be equal to phi, capital Phi y minus t, right? Where capital Phi is defined as before, right? And the Hessian is going to be equal to, anyone? Anyone remembers when we derive nonlinear least squares? What's that? All right. Phi, I'm going to call a matrix R times phi. And that matrix R just defines a diagonal matrix. Let's see. Where R is a diagonal matrix with entries in the diagonal, let's call them II, right? With entries, anyone? Yi minus 1i, yi, right? Makes sense? Because that's what we have right there. So putting this together, we have that w at k plus 1, it's equal to w times k minus phi transpose r phi inverse phi transpose y minus t. Okay? Now let's rearrange terms a little. So this is just our solution that I have here. I'm just substituting the terms over here. Okay? No, over here, excuse me, right? Substituting h and the gradient, right? That's what I think, correct? And now let's rearrange terms a little. I'm going to say that this is equal to phi transpose r phi inverse, right? This is this term right here, times phi transpose r phi wk, oops, w, no sub k, subscript k, and negative phi transpose y minus t, right? These two are exactly the same. And now this is then equal to phi transpose r phi, okay, going so fast that my writing keeps getting worse. Inverse times, let's see, now I have this term here, which I can simplify to phi transpose times r z, where z it's equal to phi w at time k minus r inverse z. No, r inverse y minus t. Okay. Anyone can tell me what this solution looks like? What do you call this solution? So I put this term apart because this is just nothing else than a term, right, that we can compute, right? This computable given our data, right? And then we end up with this. This is the result that we iterate. And what's the solution right here? Right? Someone back there wanted to say something? Come on, what's the solution? Right? Let's take R out. Let's eliminate R, okay? Take R out. What's the solution now? least squares. What is R? Anyone can tell me what R is? It's a diagonal matrix. So what's this diagonal matrix going to do here? It's going to add what? Scale weights to each of the features or dimensions, right? Or parameters, right? And therefore, this is a weighted least square solution. So this is weighted least squares. Isn't least squares amazing? I mean, it keeps popping up again and again and again. And just to think that Gauss defined this in, whenever that was, so many years ago, centuries ago, right? It's incredible. Okay. Now, if just a side note, let me finish with a side note to this. Note that I could have derived the same equations I've derived here. This has to be iterated, right? But I could have derived the equations based on our square norm, right? Or square law, excuse me. Right? So I sum over I of Ti minus W transpose phi of Xi square, right? Let's see, square laws. And if you redo everything with the square laws, you're going to end up with, again, we are going to have this term here, right? Right? So now we're going to use this, but with this new criterion, right? With the square laws criterion here. Then the gradient of this function is going to be equal to phi transpose phi, capital Phi, that is, of course, W minus phi t. And the Hessian is phi transpose phi. And now we're going to substitute this in here to get my new equation. So hence, if I substitute, then I obtain that Wk plus 1 is equal to Wk minus phi transpose phi inverse times phi transpose phi Wk. Okay, I need space. Where was I? Phi Wk minus phi transpose t, right? I only substituted these two new terms that I computed from this criterion that we had before using the square laws. I substitute them here. That's what you have, right? So far, so good. And now if we rearrange terms, this is equal to phi transpose phi inverse times phi transpose t. Wow. Now we've eliminated the weights. And we're back to least squares, right? Because I'm using the square norm, right? Which leads to least squares. Duh. Big deal, right? So both for regression and classification, right, for ridge regression and logistic regression. Logistic regression is the same, but applied to classification, right? Then the solution is either the least squares or the weighted least squares, right? That makes ridge regression and logistic regression, right, for either regression or classification. Don't be confused by logistic regression as a regressor, but as a classifier, right? That makes it very popular, a very popular solution, because it can be computed so easily, right? It's just straightforward to compute these results. So you will see people comparing their methods to, if they do regression to ridge regression, if they do classification to logistic regression, because this is just straightforward to compute, okay? All right, any questions? All right, no questions? Okay, so I'm going to move next to multi-objective optimization. So until now, we have treated this as a single objective function that we need to optimize. I want to briefly talk about multi-objective optimization, which means that we have multiple objective functions that we want to simultaneously optimize. And after that, I want to briefly talk about manifold learning as well. All right? Okay, I'll see you Thursday.